this lecture we have to see the synthesis of Longifolene by E.J. Corey and co-workers. In last lecture we saw the disconnection of this synthetic root, that is by E.J. Corey and co-workers. We have saw the structure of Longifolene and first retrosynthetic root for this synthesis of E.J. Corey and co-workers. Now in this section we have to see the synthesis of this molecule, and we know that by disconnection we have obtained the ketone molecule, that is Villain mixture ketone. That compound is known as Villain mixture ketone. That we know that we have obtained that molecule by the Robinson annulation of 2-methyl cyclohexane 1,3-diol. So that gives rise to Villain mixture ketone, and that Villain mixture ketone is a starting material for our synthesis. Now, first synthesis start with it contains 2 carbonyl group. So 2 carbonyl group, first we have to work on this carbonyl group. This carbonyl group we have to convert it into first carbon chain, and that carbon chain must be there must be diol formation, and that diol formation we have to protect here. One by one we will see that first here we have used diol compound. First we have used here diol compound. Ethylene glycol. So that glycol molecule we have used here first. When this glycol molecule first we have used, that glycol molecule the first step, and in the second step we have to use Wittig reaction, PH3P double bond CH3. What is this Wittig reaction for? This reaction is for conversion of carbonyl to double bond C group, double bond CH. Okay. Now this carbonyl group we have to convert. But first, when this react with unconjugated, this diol react with unconjugated carbonyl group. Out of these 2 carbonyl group, it react with unconjugated carbonyl group. So convert it into, see here this unconjugated carbonyl group. Here CH3 group is there, and this unconjugated carbonyl group gets protected here by using diol. So this diol we have used here to protect this carbonyl group. And now this second conjugated carbonyl group now react with this Wittig reagent, and it gets converted in this way, CH and this CH3. So this is the first step. Here in the first step again we have to add another reagent, that is osmium tetroxide. This is osmium tetroxide, and this osmium tetroxide we know that we use this reagent for diol formation against carbon-carbon double bond. So here there is a diol formation. So this protected group is here, CH3 group as it is, and this protected group, that is CH3, here double bond, here OH, CH, CH3. Let's see for understanding here, I am writing here CH. Okay. Now here is a diol formation by using osmium tetroxide. Now this diol form gets protected when we use another reagent, that is TSCl, tosyl chloride. When we use tosyl chloride here, then what happens? Out of these 2 OH group, one of the OH group gets protected. But which will protected? This secondary group, less-handed group, secondary OH group gets protected here. So OH gets converted into OTS. So OTS. So this is actual step first. There, in this step, we have used Villain mixture ketone that can be obtained by Robinson annulation of 2-methyl cyclohexane 1,3-diol. So this Villain mixture ketone, when treated with this diol compound, it is treated with this diol compound. There is a protection of one carbonyl group. Another we have used a Wittig reagent. That reagent react with this carbonyl group, another carbonyl group, and to form a carbon-carbon double bond. this carbon-carbon double bonded compound when treated with osmium tetroxide, it gets there is a diol formation, and this diol formation again when we use the protecting reagent TSCl, tosyl chloride, that tosyl chloride reacts with this and one of the OH group gets protected, and that is the secondary OH group which is protected here. So this group protected here, secondary group protected. Now when this secondary group protected, in the next step we have used base. Secondary in the second step, this actually these four reagents are used in first step. In the second step we used base here. OH minus is the base. So this base, when we used here this base, so this base removes this proton OH, so O minus here. When this reversal of negative charge, there is a breaking of this bond, and this breaking of bond leads to attacks on this CH and removal of OTS. So this is simplest reaction. The ring expansion reaction occurs here, that is pinacol type of rearrangement. So pinacol reaction is there, pinacol rearrangement is there. This O minus, this base removes proton from oxygen OH group, and O minus attacks on this bond, and the breaking of this bond when broken, it attacks on the CH and this removal of this OTS group, that is leaving group, and expansion of the ring. And at the same time we have used second H plus in presence of H2O. So H plus H2O removes this protection, because this protection is required. It must not interfere with some other reagents we are using here, osmium tetroxide, TSCl. So it must not interfere with the reagent. That's why we have to protect this group. So we protected this group for some time, and then again deprotection by using this reagent. So when we apply these reagents or pinacol rearrangement, then one 6-member ring is there, another another 7-member ring is there. See here, other group remains as it is, CH3, and another carbonyl group, that is deprotected carbonyl group. That deprotected carbonyl group remains as it is. After deprotection, it remains as a carbonyl group. So this double bond is here. Due to this, the carbonyl group is shifted here. The attack on this carbonyl group shifted here, and this bond shifted here, CH, and now CH3 group gets attached here. But here in this case, if you observe the carbonyl group is here and double bond is here. There is no conjugation, so it can be readily converted into conjugated molecule. It gets readily converted into conjugated molecule by shifting of this hydrogen. So hydrogen gets shifted here, and the molecule is converted into conjugated molecule. So conjugated molecule, we have to write this molecule here. So double bond, and here so this molecule 7-member ring, and this double bond is shifted here. This CH3 group is there, and this carbonyl group is there. Now this is actually the compound third in the retrosynthesis. Sorry, compound second in the retrosynthesis. So this is actually second compound. So we convert it into some another form. Here 6-member ring. See here, this is 6-member ring. 6-member ring. Now this is the 7-member ring. This is 7-member ring. The another one 6-member ring. Now this carbonyl group is there. This carbonyl group is there. Now this CH3 is present here, CS3, then CS3, now C1, 2, 3, 4, 5, 6, this is now 7, now this 8, 9, 10, this 11, okay, 11 carbons. Now look at this, we have to number it from the double bonded compound. So see here, numbering start from this joining carbon, so which connects these two rings. So numbering starting from here, 2, 1, here numbering from 7 membered ring. So for the sake of conversion, see here numbering from 1, here 2, 3, 4, 5, this 6, 7, then here we are writing number 8, 9, 10, and then 11. So this is actual numbering pattern. Now in this numbering pattern we have converted this numbering pattern here is 7 member ring. So we have started numbering from this 7 member ring 1 for connection. Connected carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So see here we have to attach groups here. So 1, here 2 contains CS3, 3 no any group, 4, 5 carbon contain carbonyl group. So carbon number 5 contain carbonyl group, carbon number 6 as it is, which contain carbon number 6 contains CH3 group. So it is CH3 group here. Carbon number 7 contain 7 contain double bond. So this is the actual conversion. Now simply this molecule, next reaction is the Michael addition, intramolecular Michael addition, which converts these two rings, a bicyclic compound into tricyclic compound. So it converts bicyclic compound to tricyclic compounds. So by Michael addition, we have to use the base, that is Et3L, at very high temperature. At high temperature, this base removes proton here, which can be stabilized by delocalization. So which attacks on this, and again there is a conversion of this compound into bicyclic compound into tricyclic compound. So it gets converted into tricyclic compound. See the reaction here. This tricyclic compound easily gets converted and stabilized. Remaining group as it is. Here CH3 group is there. This carbonyl group remains as it is, and this is CH3 group here. This CH3 group, and now bond gets attached here. 7 to 10 bond formation. Carbon number 10 and carbon number 7. There is a bond formation. So this type of bond formation leads to the this structure. Now in the next step, we have to protect against one of the group. Protect one of the group, one of the carbonyl group we have to protect. But before that, here we must introduce another CH3 group according to the structure of Longifolene. So how can we introduce CH3 group? We have to use first base. So we have used here base PH3CLI. So PH3CLI is a stabilized base that we have used here, which removes proton from here, and then we have used CH3I, methyl iodide. So this attacks on the CH3, and there is attachment of CH3 here, and we get the structure formation here. We get the structure formation. So CH3, another CH3 get attached here, and double bonded O. Then here carbon, oxygen double bond, then CH3. So this type of compound we obtain. That compound we obtain in this stage is again next. So we have to convert this compound, because we don't want this carbonyl group, and we have to convert this group into CH2. So to convert that, we have to use thioketone, SHCH2, CH2, SH, which protects this group thioketal. Then in the second step, we have to use some reagents that. So here we have used this protecting reagent. Second, we have used lithium aluminium hydride. This lithium aluminium hydride is for reduction of carbon, another carbonyl group, and we have used then NH2. So this NH2 utilized here in presence of base OH minus and heat. This is for removal of this ketal group and introduction of hydrogen is there. So by adding these reagents, we obtain the compound see here. This CH3 remains as it is. This CH3 group here, from this as it is, another CH3 group is here as it is. This CH3 remains as it is. Now this carbonyl is first converted to thioketal, this type of conversion, and when we use NH2 OH minus, the removal of this and introduction of hydrogen. So removal of this and introduction of hydrogen. So total there is removal of carbonyl group. Overall product is a removal of carbonyl group. So carbonyl group gets removed from here. So carbonyl group removed and another lithium aluminium hydride used. So that lithium aluminium hydride used here converts this into OH group. Now in the next step we have to convert this OH group. Now remaining is the only OH group conversion to double bond CH2. So in order to convert that, we have to use Wolff-Kishner condition. Wolff-Kishner condition in which chromium 6 is used, which converts again into carbonyl. That carbonyl, this is first Wolff-Kishner condition, and second is again we have used the molecule that is CH3Li and H plus. So under Wolff-Kishner condition, this is first converted into carbonyl, and then by using CH3Li, we are having introduced this CH3 group here in the form of CH2. So the final product obtained in this case so by using Wolff-Kishner condition, this carbonyl, this OH group first converted into carbonyl group, and that carbonyl group gets converted here. In this case, we obtain this compound. If we look at this compound, give number 1, 2, 3, 4, 5, 6, 7, then 8, 9, this 10, 11, this carbon number 12, and this is 13, this is 14, and this is 15, double bond CH2. So this compound obtained, and we know that this compound is a Longifolene. So this is first successful synthesis of Longifolene obtained by E.J. Corey and co-workers in 1954. So this is overall synthesis of Longifolene by this route, in which we have used the first compound, that is Wieland mixture. Ketone is a starting material for this synthesis. In this synthesis, Wieland mixture ketone first treated with this diol compound. This diol compound is utilized for the protection of this carbonyl group. Then we have used Wittig reagent, which reacts with the second carbonyl group and gets carbon-carbon double bond gets converted. So carbon-oxygen double bond gets converted into carbon-carbon double bond. Here converted. Then osmium tetroxide used, which converts it into diol. Double bonded compound gets converted into diol. This diol react with TSCl and less hindered, that is secondary secondary hydroxyl group gets protected, that is TS, tosylated. In the next step, we have used base here by Pinnacle rearrangement. By Pinnacle rearrangement, the base is converted into the 6-membered ring is converted to 7-membered ring, and that 7-membered ring compound expansion by Michael addition it is converted into this compound, and introduction of CH3I here.